This week, you're going to be performing Experiment 4, the determination of the percent by mass of the components in a mixture by thermogravimetric analysis. Now, thermogravimetric analysis, or TGA, is a technique employed when you want to monitor the mass of a substance or mixture while heating it. In this way, TGA allows you to determine or examine the thermal stability of the compound or mixture under question. We're going to be applying this technique of TGA to a problem much like the one illustrated here. That is, you are given a vial containing a white powder and told that it contains both potassium hydrogen carbonate and sodium chloride. Now, if you recall, potassium hydrogen carbonate and sodium chloride are both white powders. Okay, so when they're mixed together, we have a very much an indistinguishable mixture of the two components. Okay, you can't distinguish one component from the other, and so because of this, we have to use TGA to answer the ultimate question that we're asking, which is what portion or percentage of the powder is the potassium hydrogen carbonate and what percentage is sodium chloride. We can answer that using the TGA technique. Now, I should mention at this point that if you don't feel comfortable with reaction stoichiometry, there's an additional video on the Canvas course page called Grams to Moles Introduction to Stoichiometry. Okay? To understand what we're going to be talking about in this lecture video, as well as being able to effectively use the data that you're getting in lab, you really need to have a good understanding of reaction stoichiometry. So if you're not quite there yet, head on over, watch this video. It was made for us by Professor Statler. It's a great resource if you're not feeling quite comfortable yet with stoichiometry. So back to our question. Okay? We want to distinguish, or we want to determine what percentage or portion of the mixture is potassium hydrogen carbonate and what percentage is sodium chloride. And the way that we're going to be able to do that using TGA is by exploiting the thermal stability difference between the two compounds. Potassium hydrogen carbonate decomposes readily upon heating to potassium carbonate and carbon dioxide and water vapor. And this all happens at less than 100 degrees C. Now, sodium chloride, under the same amount of heating, will stay solid sodium chloride. In fact, sodium chloride doesn't become molten until 700 or 800 degrees C. So while potassium hydrogen carbonate decomposes readily under fairly mild heating conditions, sodium chloride does not. And we can exploit this difference and monitor mass loss while we're heating the mixture of the two. And the reason that this helps us is because if you'll notice here, as potassium hydrogen carbonate decomposes, as I said earlier, we form CO2 and water vapor. And since these two are in the form of a gas, they will leave as the reaction proceeds, and we will expect a mass loss due to that. So by continually monitoring the mass, we will be able to determine how much CO2 and water leave. Keeping that information in mind, we can work backwards using our knowledge of stoichiometry to figure out how much potassium hydrogen carbonate must have been there to start with to produce the X amount of CO2 and water vapor that was lost. Our general reaction scheme looks like this. You're going to have a sample, which you're going to put into a container called a crucible. And a crucible is just a ceramic cup that can withstand high temperatures, so it's great for applications like this where we're heating. You're going to weigh that. You're going to heat it. You're going to let it cool, and then you're going to weigh it again. And then you're going to repeat the cycle. You'll go back, you'll heat it again, let it cool, weigh it, heat it, cool it, weigh it. And you're going to continue this process until the mass no longer changes between the heating cycles. So what are we doing by undergoing this continual heating weighing cycle? Well, what we're doing is trying to to decompose all of potassium hydrogen carbonate in our mixture, and by weighing and continuing to heat and weigh until we no longer have any mass loss, we are determining when all the CO2 and H2O has been lost that is going to be lost. In other words, when is the all of the potassium hydrogen carbonate decomposed that's available to decompose. And so this is also called heating to constant mass, okay, until we don't see a mass change anymore. So this is the general process for your experiment this week. Now there are a couple things I want to point out about this illustration. First, I've shown a Bunsen burner here for the heating. And while you will use a Bunsen burner to clean and dry your crucible at the beginning of the experiment, you will not use a Bunsen burner to do the heating of your sample. Okay? Our Bunsen burners are so hot that they're actually too hot for this experiment and don't allow us to get accurate results. So instead, we're going to use hot plates. And at the very end of the lecture video, I'll talk about the specific settings you should use on the hot plate in place of the Bunsen burner indications in your lab manual. The other thing I want to point out here is that I have included this letting your sample and crucible cool step for a reason. It is absolutely crucial that you let things cool before you weigh them on the balance. Okay. Things that are hot have convection currents, which can cause erroneous readings on the balance. So you absolutely need to let this cool back to room temperature before weighing it. Always weigh things at room temperature. Okay, so let's suppose that we have done this. We have taken our sample, we've recorded a mass, we've heated it, cooled, weighed it, and then we've done all of this over and over again until we no longer have any mass change occurring. That tells us that we've decomposed all the potassium hydrogen carbonate that we are going to decompose, and all the CO2 and water, therefore, has left that's going to leave. At that time, we can take the final mass of our mixture and we can subtract that from the initial mass. Right? That change in mass, that mass loss, has to be due to losing CO2 and water. Nothing else here is going to cause the mass to change besides the loss of CO2 and water. So we can attribute this total mass loss to these two products, CO2 and water. Now, how does that help us? Well, we know the total mass of CO2 and H2O lost, but that alone doesn't help us unless we understand the stoichiometry of the reaction. By using the amount of CO2 and H2O lost, along with the stoichiometric ratio of how much CO2 and H2O are formed per 2 moles of potassium hydrogen carbonate that decompose, we can work backwards to figure out how much potassium hydrogen carbonate we started with in that mixture. Let's see how we're going to do that. Alright, well remember that 2 moles of potassium hydrogen carbonate decompose to give 1 mole of potassium carbonate, 1 mole of carbon dioxide, and 1 mole of water. What we're going to do is come up with a conversion factor, a unit factor, that will allow us to convert the mass of CO2 and H2O lost back to how much potassium hydrogen carbonate we had to have been starting with. And in order to come up with that conversion factor, we're going to rely on these stoichiometric ratios that we just pointed out. So let's start by determining the mass of carbon dioxide lost per gram of potassium hydrogen carbonate decomposed. Now it doesn't really matter that we choose a gram here. We could really choose anything. But a gram's a nice even number, and it's a good unit value. All we're really doing is saying per gram of potassium hydrogen carbonate decomposed, how much CO2 are we going to make? Okay, so the ratio will be the same whether you chose 5 grams here, 10 grams, or 100 grams, etc. Okay, but we're going to choose 1 gram for simplicity's sake. So 1 gram of potassium hydrogen carbonate decomposes. We can't compare that directly to the mass of CO2 formed, right? But we can compare moles directly. So what we have to do is convert our 1 gram of potassium hydrogen carbonate to moles of potassium hydrogen carbonate, and then to moles of CO2, and then back to mass. So we take our mass of potassium hydrogen carbonate, and we divide it by the molar mass of potassium hydrogen carbonate. Then, realizing that 1 mole of CO2 is formed for 2 moles of potassium hydrogen carbonate, we can apply the molar ratio of the two to get to moles of CO2 that are formed, and then multiply by the molar mass of CO2 to determine the mass of CO2 is formed. Again, this means that 0.220 grams of carbon dioxide form for every 1 gram of potassium hydrogen carbonate that is decomposed. And since this is a gas, we can also think of this as 0.220 grams CO2 lost per 1 gram of potassium hydrogen carbonate that decomposes. We can do a similar type of calculation for water. So for 1 gram potassium hydrogen carbonate that decomposes, we divide by our molar mass to get it in moles of potassium hydrogen carbonate, use our stoichiometric ratio of water to potassium hydrogen carbonate, which is the same as it was for carbon dioxide and our reactant, and then multiply by the molar mass of water to get us to the mass of water lost for 1 gram of potassium hydrogen carbonate that decomposes. Okay, taking these together gives us the total mass loss that we would expect for CO2 and H2O per 1 gram of potassium hydrogen carbonate that decomposes. This in turn gives us our unit factor, our conversion factor, right? So for every gram that decomposes, we form 0.310 grams of carbon dioxide and water. We can now apply this conversion factor to the mass that we found earlier that had been lost due to the decomposition, which we know has to only be from CO2 and water. So we apply our conversion factor to the mass lost due to CO2 and water, and that tells us how much potassium hydrogen carbonate must have been in our original mixture, so 0.206 grams in this example. Alright, so we know how much potassium hydrogen carbonate was in our original mixture. We are 90% of the way there. That's the hard part. But we're not done, because the question was to determine the percent by mass of potassium hydrogen carbonate and sodium chloride in the original mixture. And so to get a percent, right, we take our mass of potassium hydrogen carbonate that we actually had, and we want to divide that by the total mass of our mixture, right? Times it by 100, you get a percentage. Okay, that's what we're looking for, right? Well, not quite. It's a yes and no. While we have the correct mass of potassium hydrogen carbonate here, this mass for our total mixture mass is completely incorrect. Okay? I made this mistake to show, to illustrate a point. Right? This mass comes from the mass of the crucible plus the mixture. But of course, we don't want the mass of the crucible in there. We want just the mass of the mixture. So it's absolutely crucial that you account for the mass of the crucible. And one way to do that is by weighing it at the beginning before you start, so that you can subtract it out from your mass of the crucible plus the mixture. Alright, so let's say that we had weighed our crucible. It was 4.5634 grams. We subtract that from the mass of the mixture plus the crucible to get our initial mass of the mixture. And I should point out, this is the initial mass of the mixture, not the final, right? We want to know how much potassium hydrogen carbonate was present out of the original mixture. After you've decomposed it, of course, there's no potassium hydrogen carbonate left. Okay, we want to know in the original mixture what was the percentage. So we've got our mass of just the mixture now, because we subtracted out our crucible. Right, we're going to put that in as our mass for our total mass of the mixture here. Multiply by 100, and we'd find that in this particular example, we had 22% potassium hydrogen carbonate in our mixture. Now, the other part of the question was, what percentage is sodium chloride? Well, these are the only two things in there, potassium hydrogen carbonate and sodium chloride. So whatever percentage is potassium hydrogen carbonate, the remainder must be sodium chloride. So when we have 22% of one, we have 78% of the other. And there you go, we've answered our question. All right, so this week in lab, you're going to be doing something very, very, very similar, okay? Except that you're going to be dealing with a mixture of sodium hydrogen carbonate and potassium chloride. Now these two behave in much the same way as the components we just looked at. A sodium hydrogen carbonate under a reasonable amount of heat will decompose to sodium carbonate, carbon dioxide, and water vapor. And like sodium chloride, potassium chloride under heating, under the same amount of heating, will not decompose. Okay, so the sodium hydrogen carbonate will decompose, and in much the same way as what we observed with potassium hydrogen carbonate. Potassium chloride will not decompose under the same heating conditions. And again, we're going to exploit this difference in thermal stability in order to find out the percentage of each in the mixture. Some final reminders before we go for the day. You will be using some 6 molar HCl in this experiment, which is pretty nasty stuff. Okay, so you want to be very, very careful with this. Of course, at all times you should have your goggles on in the lab, no exceptions. But also, if you ever get any on you, if you spill some on your hand or your arm, make sure you get it under some water immediately and wash the area where you spilled it with copious amounts of water. Okay, and let your TA know. If for some reason you were to splash it on your face or splash it all over your person, okay, in that case, make sure you know where the eye wash station is as well as the safety shower and that you know how to use them. If you don't know how to use them or where they are, talk to your TA before the beginning of the experiment. The next thing you should remember is to always weigh things at room temperature. As we mentioned, hot objects can produce convection currents that mess with the balance and will give you erroneous readings. So always weigh things at room temperature. Also, as I mentioned earlier, you're going to be using hot plates instead of Bunsen burners for your general heating. Now, at the beginning of the experiment, when you're cleaning the crucible and drying it, you will be using a Bunsen burner for that. But for the remainder of the experiment, when you're actually heating your sample, you're going to want to use hot plates. The gentle heating should be done at a setting of 180. Okay? Your lab manual refers to it as gentle heating with the Bunsen burner. For that part of the heating, you're going to use a setting of 180 on the hot plate. When it says vigorous heating, you're going to be using a setting of 250. Now these settings apply to the new hot plates. So these are the large surface area stir hot plates. So make sure you're using one of those. If you need to, you can always share with the neighboring group. Okay? Just make sure you line up when you're doing the gentle and the vigorous heating. But make sure you use the new hot plates. These settings do not apply to older hot plates, and so if you choose to use one of those, you're going to have to do a little of experimentation to figure out what settings will work for you. And then, of course, make sure you run 2 trials, at least. Always remember, the more trials you run, the more likely it is that you're going to get accurate data. All right, that's it for this week. Enjoy Experiment 4 and performing thermal gravimetric analysis.